κάτσε γιατί πρέπει να... Δεν έχω μπροστά μου το... Okay, so welcome everyone. Okay, just give me 1 minute. Okay, welcome everybody. Today our speaker is Manolis Tsakiris from the Chinese Academy of Sciences, who will speak about Castelnuovo-Mumford regularity of subspace arrangements. So, Manolis, welcome. You can start.
Thank you very much for the invitation. I would appreciate if you interrupt me at free will, and this is also a good way to check that the connection is active. Because sometimes I'm having connection problems.
Mm.
Okay, so as promised, the first talk will be more introductory. 1 moment, please. Okay, it will be more introductory. And the second talk will be more, let's say, more special. Okay, so I will be working over a polynomial ring, which will be denoted by S, and that's a polynomial ring in R variables over a field K, and I will consider the standard grading on S. So the degree of xi is 1. And with this grading, S is can be seen as the direct sum of its graded components. And so the ith graded component of S is the K vector space of polynomials of degree I. And M is going to be a finitely generated, graded S module. So M is the direct sum of its graded components. So bracket M with subscript I is the homogeneous component of M of degree I, and this is a finite dimensional K vector space because M is finitely generated, and this grading is compatible with the module structure of M, the structure of M as an S module, and that means that the action of the ith graded component of the ring S on the jth graded component of M lands inside the I plus jth graded component of M. For such a module, we have the Hilbert function, and the Hilbert function of M is a function from the integers to the integers, and it takes an integer j to the k dimension of the degree j homogeneous component of M. And as I mentioned, this is a finite number because M is as a finitely generated S module. Now, it is very well known that this Hilbert function eventually is a polynomial. So the values of this function for large enough degrees are given by a polynomial, and this polynomial, let us denote it with P subscript M, and that's called the Hilbert polynomial. So the Hilbert function of M at J is equal to the Hilbert polynomial of M at J for every J large enough. We can also define the main invariant of interest. And that is the Castelnuovo-Mumford regularity. The Castelnuovo-Mumford regularity was originally introduced by Mumford in 1966 on a shift theoretic context, and the adaptation of this notion to commutative algebra was done by Eisenbad and Goto in 1984. There are several equivalent ways to say what the Castelnuovo-Mumford regularity is, and perhaps the simplest is by means of a graded minimal free resolution of M. So let me write this down. So graded minimal free resolution of M. So M is a finitely, let me talk about this resolution. Let us, M is finitely generated. So let's say it is generated by Vita 0 elements. So there's a surjection from a free module of F0 of rank Vita 0. So Vita 0, let's say, is the number of minimal generators of M. So this F0 as an S module is isomorphic to S to the Vita 0. But if we keep in mind the grading, and so we ask that this isomorphism of F0 with S as a free module is this description of F0 as a free module as a direct summand of free modules of rank 1. If this is a graded, an isomorphism of graded modules, then it is isomorphic to a copy of the polynomial ring shifted in degree, let's say alpha 0, 1. Then another copy of the ring shifted minus alpha 0, 2, and so on. Vita 0 of them. And there can be multiple summands that have the same shift. And this shift simply says that we have M has a minimal generator, homogeneous generator of degree alpha 0, 1. Then it has another one of degree alpha 0, 2, and so on. Now, the kernel of this surjection from F0 to M is a finitely generated graded S module. So in the same way, it admits a surjection from a free S module F1, which as a graded S module is isomorphic, say, to S shifted by minus alpha 1, say 1, and so on. Let's say there are Vita 1 such summands. And in this way, we keep going, and we get a minimal, what is called a minimal free resolution. And Hilbert's CZG theorem asserts that this complex that we will get is going to be finite of length at most equal to the dimension of the polynomial ring, which in our case is little r. Can you hear me okay?
Everything's fine.
Yeah,
Okay,
No problem.
great. So if we have then such a graded minimum free resolution f, then the regularity, Castelnuovo-Mumford regularity of M, is the maximum of the following. We look at the maximal degree of a minimal generator of Fi. So the degrees of the minimal generators of Fi in this notation, they are alpha I1, alpha I2, up to alpha I beta I. We take the maximal and then we subtract the homological position, so minus I. And this quantity, the maximum of those differences across I, is the Castelnuovo-Mumford regularity. And so this is known as the syzygetic description, because the minimal degrees of generators of the free modular position I are exactly the degrees of its minimal generators are exactly the degrees of the ith syzygy module of M, which is the kernel of the map in the free resolution at position I. Now, we can use this definition to say what the Castelnuovo-Mumford regularity is using the Tor functor. So the regularity of M is the maximum over all i's of J such that the homogeneous component of degree J of the ith Tor between M and the field K is different than 0. And the argument is simple. To compute this Tor, this ith Tor between M and K, here let me say that this field K is an S module. If we view K as S mod M, and this M is the maximal homogeneous ideal. So indeed, the quotient is just the field, and by definition of Tor, this ith Tor is the homology at position I of, we take the free resolution, the minimum free resolution, or a free resolution, but in particular the minimum free resolution of M. Then we tensor it over S with K, and then the homology is the Tor. And because of the construction of the minimal free resolution, the differentials in this complex F tensor with K, the differentials are all 0 because the maps, so let's say from Fi plus 1 up to Fi, so this map is a map of free modules of finite rank, so we can view it as being represented by a matrix whose entries are inside are homogeneous polynomials, and none of them is constant because the resolution is minimal. So if we tensor this map with S mod the maximal ideal, then this map will become the zero map. And so this homology at position I is actually the entire module at position I. And this is just Fi mod MFI. And so this is a finite dimensional vector space, and the largest degree at which this is non-zero is this J that we're looking at here. And the largest degree that this module here is non-zero is exactly the largest degree of a minimal generator of the free module Fi. Okay. And using this, we can also describe the Castelnuovo-Mumford regularity in terms of causal homology. So causal homology description of the Castelnuovo-Mumford regularity. Well, first of all, we have the causal complex associated to the variables. I will not mention the definition of the causal complex, but I'm happy to do so if anyone wants. So we have this causal complex, and this is a minimal free resolution of K, of S mod M. If we tensor this tensor complex, this causal complex with M over S, then we get a complex which need not be exact and whose homology at position I is called the ith causal homology and denoted like this. And the Castelnuovo-Mumford regularity of M is the maximum across I and J of the difference J minus I, such that the ith causal homology of M at degree J is different than zero. And as a way of an argument, how does this follow from, let's say, proposition 4, is that, well, the causal complex is a minimum free resolution of K. So if I want to compute the Tor, if I want to compute the Tor, the ith Tor between M and K, I can just take a free resolution of K this time, which is the causal complex, and tensor it with M. And that's exactly what I will have, will be exactly the causal homology. So okay. This is nice because the causal complex is very easy to construct, while constructing the graded minimal free resolution of M and seeing what the degrees of the various modules R is not equally easy. Yet another description, and in fact the one given by Eisenbach and Goto, is a local cohomology description. And according to this, we have that the Castelnuovo-Mumford regularity of M is the maximum of I plus J, such that the ith local cohomology of the module M supported on the maximal homogeneous ideal little m at degree J is different than 0. And this object, as I mentioned here, is the local cohomology module. And let me tell you what that is. So the ith local cohomology of M of the module M supported at the maximal homogeneous ideal little m itself has various equivalent descriptions, but perhaps one of the easiest ones is to form the Čech complex. So Čech complex on the R variables. Again, I will not say what the Čech complex is, but I'm happy to do it if I'm asked. So we take the Čech complex on the R variables. We tensor it with M, and so we get a new complex. And the ith cohomology of this complex is the local cohomology of M supported at the maximal ideal M. And again, that's quite easy to construct. Another way to define a local cohomology is via injective resolutions, but I will not talk about that. And so we see that we have quite different. Okay. I see. I see a question which asks what the Čech complex is. Okay, so very quickly, let's say what the Čech complex is. So if I have the Čech complex on, let me tell what the Čech complex in one variable is. So the Čech complex in one element, let's say x1, is the following complex. It's very simple. We start from S, and then we consider the canonical map from S to the localization of S at x1. So we have inverted one variable. So then the Čech complex in R variables is the tensor product of the Čech complexes of each of the R variables. Tensor product of complexes. And this looks like this. We start from the polynomial ring S, then we go to the direct sum from I equals 1 up to R of the localizations of X at Xi. So we have the direct sum where in each summand we have inverted one variable. Then we go to the direct sum over, let's say, I less than J, where now we invert two variables, so Xi, Xj. Then we invert three variables, Xi, Xj, Xl, let's say, and so on, up to at the last position, we have inverted all the variables. So it's just xs localized at x1 times up to xr. And then, as I mentioned, if we tensor this complex, this complex has homology only at the end. But if we tensor it with M, then we get a non-exact complex. And it turns out that the local cohomology module here, the local cohomology module of M, is the ith cohomology of this complex. And Grothendieck proved this. Grothendieck introduced local cohomology, and he proved this fact. So the only place where we need it in this talk is to just say that the Castelnuovo-Mumford regularity of M has a description in terms of local homology, which is the cohomology of this complex. That's all. And the point of me mentioning those various definitions is just to indicate that this invariant, the Castelnuovo-Mumford regularity, is an important one because it can be expressed in different ways. So various notions get connected with each other. If there's some question and I haven't seen it, please, by all means, ask me. Because I cannot look at the chat all the time. So now,
Manolis, before you continue, can you move the toolbar to the bottom right of the screen, because it's in the middle of your notes?
the toolbar.
Is it possible to move it or minimize it, and then it only pops up when you actually use it?
Let me see. Oops, no. So I think right now this is the smallest I can make it, and I'll keep it in mind. So I'll try. Yeah.
You can move it on the side of the screen, from the bottom, and that way, when you reach it, then you move to the next page. So it's not going to be blocking the. And I'm thinking about of posterity too, because this may go on YouTube, and we want it to be as clean as possible.
Is this okay now? I put it on the side.
It's great. Yes. Thank you.
Okay. Thank you very much. Now, if we go back to this definition of Castelnuovo-Mumford regularity, the syzygetic one, so the one of, definition 3, it essentially says, look at the ith free module in the minimal free resolution of M, look at the degrees of its minimal homogeneous generators, take the maximum such degree, and subtract the homological position. And then for all those subtractions, pick the maximum. Now, if we do this at position 0, so if we go at position 0, the homological position, at homological position 0, we subtract 0. So we're just looking at this alpha 0, 1, alpha 0, 2, alpha 0, beta 0, which are the degrees of the minimal homogeneous generators of M. And so the Castelnuovo-Mumford regularity, just by this, is seen to bound the maximal degree of a minimal homogeneous generator of M. So, oops, now it got, let's see, maybe I can. Do it like that. All right. So the Castelnuovo-Mumford regularity of M is greater or equal than the maximal degree of a minimal, the maximal degree of a minimal generator of M. So another way to say it is the maximal degree in which M is generated. And the importance of this fact is that this maximal degree of a minimal generator is not a quantity that behaves very well. On the other hand, the Castelnuovo-Mumford regularity, which not only bounds the degrees of the minimal generators of M, but also the degrees of the minimal generators up to a shift of all the CZG modules of M, is well behaved. For example, is well behaved on short exact sequences. So, for instance, this we will need a little later. So let me remark it. So, for instance, proposition 8. If we have a short exact sequence of graded, finally generated S modules, then similarly to the depth lemma, we have the regularity lemma, which says, for instance, the regularity of M is greater or equal than the maximum, is the other way around. It's less or equal than the maximum of the regularity of M prime and the regularity of M double prime. The regularity of M prime is less or equal than the maximum of the regularity of M and the regularity of M double prime plus 1. The regularity of M double prime is less or equal than the maximum between regularity M and regularity M prime minus 1. So as an application, as a very simple example of this statement, which is not hard to prove, proposition 8 is not hard to prove, we have that the regularity of an ideal I, viewed as an S module, is the regularity of the quotient plus 1. And to see this, one considers this short exact sequence. I goes to S, it goes to S mod I, and notes that the regularity of a polynomial ring is 0. Okay. Another very important and interesting connection is that of the Castelnuovo-Mumford regularity with the Hilbert function of M. So in particular, if you remember in notation 2, I mentioned that the Hilbert function of M eventually becomes a polynomial. So a very interesting question is, in what exactly degree does it start agreeing with the Hilbert polynomial? Because all that we have as a basic fact is that the Hilbert function eventually agrees with the Hilbert polynomial. But what is the minimal degree in which this agreement occurs? And this sometimes is called as the regularity of the Hilbert function, so a different regularity. But anyway, the Castelnuovo-Mumford regularity can be used to give a bound for this degree. So in particular, we have that the Hilbert function of M at degree J is the Hilbert polynomial degree J for every J bigger than the regularity of M. And I want to show you this. This is a textbook level result, but I want to show you the proof because it's very, let's say, nice, very cute. So Serre proved that the difference of the Hilbert function of M at degree J by the minimal polynomial, by the Hilbert polynomial, so at every degree J, this is equal to an Euler type, Euler characteristic type quantity, in particular, the sum, let's say from I equals 0 up to R, so again, R is the dimension of the polynomial ring, okay? Then we have an alternating sum, and then we have vector space dimensions. We have the K dimension of the degree J component of the ith local cohomology module of M supported at the maximal ideal. So this holds for every J, and Sarah proved this. Now, if you see this theorem 6, this local cohomology description of the Castelnuovo-Mumford regularity, if we choose a degree which is bigger or bigger than the regularity of M, the right-hand side vanishes. Okay, so that's a proof. So it can also be used as a measure of the Hilbert function regularity. And I would also like to say that the Castelnuovo-Mumford regularity also, well, let's make it remark, also can be viewed as a measure of complexity. So measure of complexity of Greber basis computations. For instance, if we have an ideal I, not necessarily homogeneous, such that the dimension of S mod I is 0. So if you wish, a zero-dimensional polynomial system of equations, and we want to solve it, the Castelnuovo-Mumford regularity enters in complexity bounds on computing a Greber basis of the ideal I. And as another remark, so now the question is, given an ideal, for instance, how big is its regularity? So from now on, let's, instead of dealing with a module M, let's look at particular cases of modules S mod I or I. So given an ideal I, how big can its Castelnuovo-Mumford regularity be? And it's a quite famous result that in general, the regularity, so this result is by combined work of Giusti in the 70s and Gallego in the 80s for characteristic 0, or Caviglia much later, 2005, for any characteristic, which says that the regularity of an ideal I, of a homogeneous ideal I, is less or equal than the following bound. twice times the maximal degree of a minimal generator of I make it a bit smaller to fit. Okay. To the 2 to the r minus 2. So a doubly exponential bound, which involves the maximal degree in which the ideal is generated and the number of variables that we have. So quite big. And while this bound is somewhat discouraging, there has been a lot of results and a famous conjecture, for instance, the Eisenbach-Gould conjecture, but also many results from well-behaved ideals, particularly coming from algebraic geometry, in which the regularity is much smaller than this doubly exponential bound. And here we arrive now at the main notion of these two talks. And I will write it as a question. What is the regularity of an ideal I such that I defines a union of linear spaces, in the projective space over the field K of dimension r minus 1. So this is the main question that we will be concerned with. And I will define more precisely how I looks like in this particular case. But before that, let me say that a major motivation for me, let's say, was when I was more of an electrical engineer than what I'm now. I was already into algebra, but I was studying algorithms for theoretically and computationally. So I was studying algorithms for what is called generalized principal component analysis. And as the term says, this is a generalization of principal component analysis. And in principal component analysis, what is being achieved is a data set is given, and a linear subspace is fitted to this data set. Now, in generalized principal component analysis, it was recognized that this is not always a good idea because a data set may be heterogeneous. It may contain subsets of sub-data sets which come from different sources, and thus it is meaningful geometrically, but also from a data science point of view, that each such subset of data has its own subspace. And so generalized principal component analysis started the research on how can we fit a union of linear spaces to a data set. But then the situation is much harder because a linear subspace is an easy, let's say, object, particularly is linear, but a union of linear spaces is not linear. And as I will mention in the sequel, is many fundamental questions about it are open. And so in particular, those algorithms, what they do And remark 14 is the only thing I'm going to say about machine learning. But those algorithms, what they do is that they take the data set and they try to find vanishing polynomials, homogeneous polynomials that vanish on this data set. And in the hope that those polynomials in low degrees agree with the polynomials that vanish on the union of linear spaces. So imagine a set of points coming from a union of linear spaces, and imagine looking at polynomials that vanish on the data set at low degrees. And if the data set is rich enough, those polynomials will also vanish in the union of linear spaces. And so the idea here is from the data set to find the ideal that defines the union of linear spaces. And once we have the ideal, we can, for instance, consider its primary decomposition and extract the primary components, which are the linear subspaces. But in order to do that, and that was the main question I was dealing with at the time, one needs to know at which exactly degree should we stop looking at vanishing polynomials. So if we have found all the vanishing polynomials on our data set of degree 3, of degree 4, of degree 5, of degree 6, where exactly do we stop? So if we know the Castelnuovo-Mumford regularity of the ideal, then this tells us that it's enough to go up to that degree. And so this is the connection then of Castelnuovo-Mumford regularity with machine learning that I would like to mention. Now, this concludes the general introduction. And before I go more, start discussing in detail question 13, I'd like to ask if there's anything I could clarify.
Okay, Manolis, I do have a question. Since you have started talking about the motivation and the computational side of your problems, so how easy is it to compute the regularity you made? I mean, computational speaking, is it easy? I mean, if I give you an ideal,
It's not easy.
It's not
So
easy.
one needs to compute, for instance, the graded minimal free resolution. And this can be done for simple ideals. But one sees that as the ideal becomes more complicated, then this computation takes longer. And just to make a connection with the particular ideals that are of interest in this talk, if we have an ideal which defines more and more subspaces in higher and higher dimensions, then this computation just becomes infeasible. And that's why it's important if we can specify it theoretically.
Okay, and another question is about the theorem 12. How sharp this upper bound is?
It is sharp. That's
okay.
Yeah. It's a very good question. It is sharp. That's why this result is that much important. Yes.
Okay. Thank you.
Okay, so if there's no other question, let me also see the time. Okay. So, all right. Then, since there are a few minutes left, I will just become a bit more precise about the type of ideals that this talk is concerned with. And next time we will start diving into them. So, all right. So, as a reminder, our polynomial ring is over R variables in the field K. And if we look at the homogeneous component of S of degree 1, this is a vector space. So the k dimension of this vector space is R, and this is the vector space of all linear forms of S. Inside this vector space, let us consider n sub-vector spaces, so k subspaces, okay, and then I'd like to say to define the ideal big I with subscript little I to be the ideal generated by all the elements in the ith vector space. So this is an ideal now of linear forms, because the generators are linear forms. And so if I look at I'm going to use this notation, V of I sub I, the vanishing locus of this ideal in, let's first look at it in the affine space of dimension R. Then this is just a linear space, this vanishing locus. And the dimension of this linear space, the vanishing locus of this ideal, is it is R minus the height of the ideal II, because you might just to give you an example, if I take VI, so example, if I take VI to be generated by x1 and x2, then the vanishing locus of VI is just the set of vectors of R tuples for which the first two coordinates are 0. Okay, that's all. And but the language I would like to use is that I would like to look at the projective scheme of S mod II. And so this now is a linear space, but I want to look at it as a linear space in the projective space. Okay. And now the ideal now that is the main, let's say, protagonist, is the intersection of those n ideals. And you see that each of those ideals, so each I sub I, is generated by linear forms. So it's a prime ideal. And that's this ideal J with, okay, I should have called it I. So this ideal I is a radical ideal because it is the intersection of prime ideals. And then the question is, what can we say about the regularity of this I? So what can we say about this? This is a good point to stop for today. But I can also keep going if we have more time. So, or if there are any, how much time is left?
Minutes, so I think
It's probably a good place to stop.
Okay.
okay, let me stop the recording.